Hi everyone, my name's Niklas. I'm from the University of Frankfurt, and I'm going to present our latest paper that's in collaboration with all of these lovely people here. We looked at Fermion-Boson-Stars, but first, what is a boson star? One of the simplest mathematical things you can do is get a complex scalar field and just assume like a free field. If you then apply the Heisenberg uncertainty relation, you get a maximum mass for this system. And if you get solar masses for for these very light masses here. So this is why we call this is called ultralight dark matter, because in this case it's pretty small masses. If you then add self-interactions, you can kind of like make your star larger. This is what's been looked into before also with other talks here, but most of them have used a kind of effective equation of state formulation for this, which requires a non-zero self-interaction. So what we have done is solve the Klein-Gordon equation coupled with the Einstein equations, and in this way we don't need to use the effective equation of state. So then Fermion-Boson-Stars, if we put a neutron star on top of a boson star, however that might happen through accretion, through mergers, if they're both there in the beginning, doesn't matter for now. So we coupled them, we solved the TOV equations coupled with the Klein-Gordon equation. And then we can choose some initial conditions, and this is what you see here. Every point here is a different kind of star with different central value for the neutron star mass, for the fermionic mass, and with different central scalar field. And not all of these are stable. You can apply some stability conditions, which is shown here. And all stars inside of here are stable, and the ones outside would either move into this region or collapse to a black hole. On this line here for zero central field, this is the normal neutron stars. And on this line here is what you get for pure boson stars. And if we plot this in a mass-radius relation, so you've probably seen these plots before a couple of times, but we just used a different color scheme because I think this looks nicer. So you have the pure DD2 here, and this is what here we plot the effective gravitational radius, which is where 99% of the rest mass of both fields combined is contained in. This gives you an idea of the compactness of the object. Down here we plot the fermionic radius, what you would actually probably see with a telescope nicer. And you can see here, in this region you have core solutions and your star gets more compact. And down here you have halo solutions. If you turn up the self-interaction, which is repulsive, the boson component expands, and you get these much larger halos around your star. At the same time, your neutron star can look much more compact. So you actually move here into this region, into the gray region, which is the Buchta limit, where general relativity tells you you actually cannot have a stable configuration. So if we ever were to observe a neutron star in this region, it might be because it's covered in a bosonic cloud. If we move up masses, if we go to lower masses for the bosonic component, it's a factor of 10 smaller, we also get stars that are a factor of 10 larger. So you can have these really large extensions in the effective gravitational radius and have what it would look like super compact neutron stars. So if we ever were to observe something like this, probably could be explained by this. We also looked at the tidal deformability of these stars. We've heard a lot about this, but just a quick recap. If you apply a tidal field to your spacetime, the star will actually develop a linear response to this tidal field. So here you have, at large radii, you have the Schwarzschild component, and here you have the tidal field and its linear response. And this is the thing that we computed. You can also make this dimensionless, so it's independent of the units. And you make a perturbative ansatz for your fields and the metric. And then you can calculate the tidal deformability, which looks like this in a mass tidal deformability plot. So here like in this white bluish region, you have the DD2 solution, and here in yellow you have the pure boson star solution. And you can see that for different dark matter fractions, they approach each other continuously. And for your core solutions, you actually have a smaller tidal deformability, and for your halo solutions, you actually increase the tidal deformability. And here for the lower masses, where you had the large halos, you can actually like increase your tidal deformability by orders of magnitude. And I see I still have some time, so I can talk about these backup slides. In principle, we could explain the Hess measurement of the unusually small neutron star with some core configuration. And we could also constrain our models with the 170817 measurement, which gives an upper bound on the tidal deformability, which we'll plan to do in the future. Also interesting for the other people here, if we compare to the effective equation of state, which is given here, I think calculated in the 80s, this expansion is only valid in the limit of large self-interactions. And you can see here this is the tidal deformability. If you go to larger self-interactions, they actually approach each other. So this is for pure boson stars, and this is for Fermion-Boson-Stars. And you can see here the larger your self-interactions, the better the effective equation of state captures your tidal deformability. With that, I want to thank you. And are there any questions?
Questions? Thanks for the talk. There is something which I don't understand conceptually. So when you solve coupled Klein-Gordon and Einstein equations, you treat your field completely classically. So no effects like Bose-Einstein condensate could appear. But the equation of state you called effective one, it's not an expansion, it's mean field approximation for that lambda fly to force theory. And it's obtained at zero temperature under assumption of the Bose-Einstein condensation. So I don't understand how something which completely misses it and something which has that effect, how they can work in a similar way.
Sorry, I don't think could you refresh that? Thanks. This is not quantized, right? This is if you look at these macroscopic configurations, you can actually treat them like a classical field, even for zero self-interaction.
Okay.
I mean, there's been a paper that I can send you.
Okay, thank you.
Any other question?
Hi. This was very nice. Could you show again the one of the first slides where you were showing about how you were kind of breaking the Bookdahl limit? Can you sort of explain that again to me? I think so. How can you're not really breaking it, right? You're just saying that observationally it looks as if you're breaking it.
Yeah, if you only observe the neutron star component, like with nicer, then it would appear to be so small, so compact.
Because the bosonic component actually has a larger mass.
Exactly.
I see. Oh, great.
Yeah. So yeah, these are like the dark matter mass fraction. The bosonic mass fraction is almost 1 here. So they're mostly bosonic stars with a small fermionic component.
I see. Okay, thank you.
Yeah. I have a question about the Hess measurement here. Could you show again the mass-to-radius relation? It seems you cannot reach two solar masses. What's going on there?
So yeah, how you would explain this is that different stars have different dark matter mass fractions, right? Depending on how they form. So some stars might have 0% dark matter. Some other stars might have 20% dark matter, and then.
But it seems you cannot find configurations that both will get these massive stars and also the Hess. I mean, with this approach, but you can even find configurations with hadronic stars or hybrid stars that will go through all here.
Yeah, it also depends on the equation of state that we use for the fermionic matter. So, I mean, you have so many degrees of freedom that you can make this look however you want to.
Okay, I think, well, if it's a very quick, I think with that we can move to, we can take the speaker again and move to the last speaker.